Alright, so this is Computer Science 305, Programming Languages, and today we're going to be talking about ML. So, we'll be operating most of this from the command prompt, but I will also have the slides off to the side here, so you guys can actually see what's going on. So those are the book slides from Chapter 5. I'm sure we're all doing our reading. I know I am. So anyway, first look at ML. First thing we want to do before we get started here and looking at the different slides is maybe we want to start ML up, right? So I'm assuming that you read the instructions prior to actually operating this video and got SML or Standard ML of New Jersey installed on your system. And so I'm going to do that by executing the command SML, and that brings me to the prompt. Shows me I'm using Standard ML of New Jersey version 110.79. It was recently built back in August. So, ML stands for meta language. It's one of the most popular functional languages, which, as it states here, is not saying that much. Is made back, as I talked about on the history lecture, that was made in Edinburgh back in '74 by Robert Milner's group. Various dialects. There's 5 major ones that I'm aware of, but there's probably even more. And that's not including that's just of ML itself, not including O camel, camel, F sharp, etc. So we'll be using standard ML. We'll just call that ML. So the first thing we want to do is go ahead and execute the statement that we see there. So 1 plus 2 times 3. And we should see, oh, sorry, I need a semicolon. Don't forget that. And that returns the val it equals 7 and its type is int, right? So kind of decomposing that down is that what's going on here is there's a special variable it. It's the return variable, right? And it's bound to so it's bound to the value of any expression you type. So the last expression that was executed is the value. Its value is the value of it, and in this case it's 7, and its type is int, right? So as just an outline of what's going on, we'll be talking about all the really basic concepts from ML. Constants, operators, how we define variables, what are these concepts, tuples and lists, how we define functions, and then we'll get a little deeper into ML types and type annotations. So starting off, right, let's just look at a constant. So 1, 2, 3, 4, semicolon, don't forget that. And that's just obviously an integer constant, right? If we were to add a decimal point, 123.4, that gives us a real, right? And so we can also have negate a number with the tilde. Sorry, wait, let's use 2. It gives us -2. So these are the basic 2 type names, right? Int and real. They're where we normally think of they would be int and float or int and double. It's real in ML. Furthermore, we can shift down to literal values for Boolean, so constants, true and false, right? They're both Boolean. It's case sensitive, be aware. You can't use capital T true or all caps true like you can in other languages similar to Python. Uses, I think, capital T true, and I think you can use either capital T true for true and false in R. So moving forward, we also have strings, right? Basic concept. So example, Fred. Note in this language that it requires it to be the double quotes. You can't get away with single quotes, but you can use things like the typical escape sequences like double backslash or \n or \t to give you what you want to see. Characters are a little odd and kind of a disgusting looking syntax. A character is indicated by a hash followed by a quote, the character, and then the end quote. And so that as I show here in the terminal, it gives us the a class or type char. Moving towards operators, it's pretty simple. A lot of for integers, right? We have the negation operator, the addition operator, the subtraction operator, the multiplication operator, and then if we want to do integer division, we use div, and then to find the remainder, we use mod, right, for modulus, and that gives us, of course, a -1. For reals, we use -1.0, the addition operator to plus. Subtraction is with the dash, and multiplication is with the 4.0. Division is with the /, and there is no obviously remainder operator. That gives us -1.4. So all these things work with type real. Now we note that they're all left associative. The precedence is plus minus is less than the times, divide, div, and mod operators, which are all lower precedence than the tilde operator. Note that this type of where these operators can be used for more than one type, that's actually a form of polymorphism we'll be talking about later. There are special operators for strings, for example, as shown here, bippity. And then the caret operator is for string concatenation, boppity boo, right? Concatenates the string and shows us that the value of it is now bippity boppity boo, one long string, right? We also have relational operators that we typically find in any other language, less than or equal to. And of course, we can do this with strings or as well as with characters. So as we see, we have characters here. We're looking at the character D is greater than the character C, which turns out to be true as expected, right? And then if we look at ABCE is greater than or equal to the string ABD, we see that's false, right? Because it follows typical alphabetical comparison, and so that the D comes after C, so therefore ABD would be greater than ABCE. So we can there's all you can use the less than, greater than equal to, less than equal to operators for string, character, integer, and real. Order on strings is what they call lexicographic. And so that kind of gets into, I would suggest you go look that up if you're unsure of what lexicographic actually means, but basically it follows an alphabetical as well as handling numbers and other non-alphanumeric characters. There's also equality comparisons. So equality is compared with a single equal sign. So 1 equal 2 is not assignment in this language, right? 1 equal 2 in this case is comparison for equality, right? So we know that's false because 1 is not equal to 2. If we want to check if something is not equal, we could actually check the greater than it's greater than less than sign. That's the not equal sign. Then we find that's true, right? But if we use the true false, we obviously know that that's false. Actually, so yeah, true is not equal to false. We know that's true. Now, the interesting thing here is if we try to use actual equality on floating point or real numbers, it gives us the error, right? Well, that's the reason is because equality is not defined for that domain. These are not equality operators, right? So you have to actually have a type that has that capability. So moving forward, we also have for our logic, right? We have the or else and also and not operators, which can then be work with equal and not equals, right? And so, but those can be used for equivalence and for exclusive or. So, and then if you look at the precedence over here, it's showing that or else as lower in precedence than and also, which is lower in precedence than all the relational operators, which is lower in precedence than our typical add, subtract, concatenation, which is lower than our multiplication and division, which is lower than negation and not, a negative number and not. So that's sort of what's going on here. So if we want to take a look at this, we can say 1 is less than 2, or else 3 is greater than 4. So now, or else is inclusive or, right? It's as long as 1 is true, then the whole expression is true. So we can see that by verifying that 1 is less than 2, or else 4 is less than 3. Oh, so we already did that. But it also and also sorry. So it does use I'm not quite sure if it uses short circuit logic, but I'm fairly certain that it does. Yeah, so it actually does right here. It says and also or else are short circuiting operations. If the first operation or else is true, then the second is not evaluated. Likewise, if the first operand and also is false, then the rest is not executed. Note that these are not operators, but they're actually keywords built into ML itself. So it should be known that all actual operators evaluate in ML. All operators evaluate all operands. So that has to be known. So if we move forward, we can actually take a look at some of this. And so we have conditional expressions, right? So we can use the standard if then else type stuff. So if we execute this inside our terminal, I'm going to scroll that up a little bit. Not what I want to do. There we go. Get rid of all these things. So we can actually see what's going on. So if we were to execute this way, if 1 is less than 2, then the sharp x, so the character x else the character y, right? Make sure you have a semicolon at the end of that. It's one whole long statement, and so the value was x, right? Because 1 is less than 2. On the other hand, if 1 is greater than 2, right, which evaluates as false, then 34 else 56. Execute that. That comes out, of course, as 56. We can, because that has a value, right? We can use that to then perform many more calculations. So similar to Ruby, right? Most things have a value that comes out. In actually everything in ML has some value. So we can use this to be 1 less than 2, then 34 else 56, and we add 1 to that value. So we know that 1 is less than 2, so it's going to return 34. So that gives us the reason to expect 35 for the value bit. And lo and behold, it was, just as shown here in the slide. So note that you always have to have an else, right? There is just no if-then construct, right? We have to have the else part. So there's something for you to do here in practice. I'm going to let you guys take a look at this. The slides will be posted. Please go through and be prepared to figure out what the value of each one of these expressions would be, as well as the types. So not just the value, but the type. Same with being able to tell me what's wrong with these fundamental expressions that are being shown here. Moving forward. Oh, a little bit too far. So as I said before, all these different operators are overloads. So plus, subtraction, less than, greater than, all those different ones. When they can operate on multiple types, we call that overload, right? It's polymorphic. So the multiplication has been overloads, taken 1 times 2, right? Gives us a value of 2. 1.0 times 2.0 returns 2.0. Now note that they return the right type, right? 1 times 2 when they're both integers returns an int type. 1.0 times 2.0 returns a type real, but we can't use this to handle an int times a real. It's not like in Java where that will automatically be adjusted to give you the correct floating point value. ML doesn't do that. It gives you, this is called strong typing. It gives you it tells you that there's an issue and you have to come up with a better way of doing this. So there is no implicit type conversion. Instead, you'd have to actually convert the type yourself. So basically casting like in Java. So we can cast or convert functions using real, which can then convert an int to a real. Floor converts a real to an int. Ceil converts a real to an int. Same with round, truncate, ord, and then ord converts a character to an int, and char converts an int to a char, and then string converts character to string. You can apply these functions as to an argument in ML just by putting the function next to the argument. And note that more often than not, parentheses, similar to Ruby, are almost never required unless there would be confusion for ML on what's going on. So, for example, we can say real 123. That converts that to a real number, 123.0. Floor truncates the decimal point, right? So the floor 3.6 returns integer value of 3. Ceil 3.6 should return the value of 4, right? Because it rounds up. Round probably follows the typical rounding rules. So if we have 3.5, that should return 4. If we round at 3.3, that should return 3. We also have ord. So if we have some character, let's say, I don't know, R, that should give us the integer value of that, assuming that it can. And that gives us the ASCII integer value for R, which is 114. If we say ord, and we give it a character value of, let's say, 1, I think that should give us the value 1. Oh, no, it gives us 49. So it does do the conversion for ASCII or Unicode, depending on how you look at it. Char should convert a number into a character. So if we have 49, and that should return 1, right, as we expected. And then we can say str on let's see what 45. That should throw an error. Yeah. So str requires, as it states there, it needs a character. So if we put in the character x, we should get the string x. So you apply the function as expected. So we already talked about that. We can actually rerun this. Str and then just without parentheses, and gives us x as expected as a string. So there's a function associativity. Like function application is left associative. So FAB means the in parentheses f of a the function f applied to a, and then that applied to b. If you need to use multiple arguments to a function, you have to provide those in parentheses. But if you only have one, then it should be fine. But be aware of that. So if we have also function application has higher precedence than any other operator, so be careful, right? So if we had some function square that took in 2 plus 1, right, which is the value 5. For example, if it says square, I don't know if that's actual word, 2 plus 1, right? Yeah, so we don't actually know what square is. But if we define square, which we'll get to in a bit here, but just for now, bear in mind, I want you, for practice, to go ahead and figure out what these are, right? We'll be aware that you might need to be able to do this. Go ahead and run these and figure out what's wrong with them inside of your own SML. And once you get done with that, you can figure out what's wrong with those, be ready to be able to describe if I give you something similar to that in class. So let's talk about defining variables. So variables is pretty easy to define in ML, but bear in mind that once you've defined it, you've bound the value to the variable, right? So if we use the keyword val, say x equals 1 plus 2 times 3, now the val x is bound to the value 7, right? So we type in just x, it gives us 7, and we say val y equals if x is equal to 7, then 1.0, else 2.0, then y is now bound to the value 1.0, right? So it does give us this nice definition of what a variable name is. Variable name should be a single letter followed by 0 or more letters, digits, or underscores. But note that it should consist of a letter initially. So now we can actually redefine the value, but we have to rebind it using the val keyword. So say val Fred equals 23. Fred is now equal to 23, right? So we Fred as expected, right? Say val Fred equals true, right? Now it's a Boolean. We again validate Fred, right? You can define a new variable with the same name as the old one, even using a different type. This is not the same. It should be noted this is not the same as assignment, right? It defines a new variable, but does not change the old one. So anything that was using the old one will still use that old value. So that's something that we should be aware of. So some more practice. Walk through that and look up what you run val a equals 1 2 3 4 5 6 for b. C is equal to a concatenated with b concatenated with 7 8 9, and then reassign the value of a equals 3 plus 4, and then run the expressions, right? What is this to a, b, and c? So anyway, moving forward, right? In interactive mode, ML wants the input to be a sequence of declarations, right? If you just type an expression exp instead of a declaration, ML treats it as if you had typed val it equals that expression, right? So if we just type in 1 plus 2 plus 3 inside of it, right? It does actually say val it equals 6, right? So if I actually type in it tells me val it equals 6, right? The interesting thing is as an interpreted language, ML does have garbage collection to handle all the memory issues that it might have. So you be aware that when you're running inside of the interpreter, you might actually see garbage collection messages coming up. That depends on, obviously, installation, how much memory you have available, and things like that. We're not going to really talk about that until we really get into Java, which has a pretty good garbage collection mechanism. So we'll start talking about then. But for now, you can just ignore that. We'll move on to tuples and lists. These are a more interesting component of ML. And so one of the things we want to talk about is what are tuples. Tuples are basically, hopefully you remember this from discrete math or the first section of theory or anywhere else in abstract algebra and math that you have ever taken and learned about these things. But tuple in ML is just, it's a type that has at least 2 elements, and they can be of any kind of type. So for example, as shown in the on the slide there, if we have the we want to create a val, we'll call it Barney, and we say it's 1 plus 2, 3.0 times 4.0, and Brown. So this is a tuple consisting of an integer, a floating real, and a string, right? Well, then the interesting thing is that becomes its actual type. Its type is an integer, real, string. It's a combination thereof. So now Barney can take on that value. And so, but when it's going to be used, when you use Barney to, for example, compare against things or something like that, you can only compare against other things that are exactly the same. If we create another one, val point, and we say it's equal to red, and then a tuple, another tuple, right? So tuples can contain other tuples. What this is basically saying now, its type is a string by a tuple, which is an integer by an integer. Now note, you cannot create a tuple of one item. right? That's just an item. It's just, as it shows here, instead of it being a tuple where a tuple is defined by something inside parentheses, this is just 2 in parentheses. That's just the number 2. So bear that in mind. We can access items from a tuple using the hash followed by a number. The index for that would be starting at 1, if I recall. So the second item in Barney, right, is the value 12.0, which is the valuation of 3.0 times 4.0. Now, interesting enough, if we want to access the second item of the internal item of 0.1, right, the first item of the second item of the second item in 0.1, we would access that by saying 1 and then 2 of 0.1, right, which would give us 300. Okay, so if we want to access the second part of the internal tuple, we say 2 of 2.1, and that would give us 200, right? So we can use these things to, like I said, we use parentheses to form tuples. Tuples can contain other tuples. It's like a record with no field names. And then we use the notation hash I, and then followed by the name of the tuple to actually access the ith element of that tuple. And as I said, there's no such thing as a tuple of 1, like one item. It doesn't exist. And that was when I was showing that if you had just 2 in parentheses, in this case they used 1, right? It's nothing. It's just it's not a tuple. It's just that individual number. So when we were creating those different individual tuples, we noticed that the type gives us is, for example, the 0.1 tuple was a string star, and then a tuple of 1 star int, right? What that's basically saying is it's these types are constructed, right, from basic types. And so we do have to note that the exact ordering and way that type is described is that specific type. So for instance, if you had an int star and then a tuple of an int star boolean, is not the same as the combination of a tuple of ints, right, 2 ints, and a tuple of ints and a boolean, right? They're not the same. And it's not the same as an int, and a boolean. So bear in mind that the way these types are constructed does matter. Now, on the other hand, lists are slightly different, right? A list is constructed using the square brackets. It's very similar to an array in other languages. In ML, unlike, for example, Ruby, an array must be all the same type. So we can create one of ints just by using square brackets separated by commas. That gives us an int list, right? I can create one of a real, right, and that gives me a real list. I cannot create one of an int and a real. That gives me an error, right? They have to be the same. So, but we can create one of like boolean or character, or you can actually create the empty list, I believe. And so note the type here is comma A. That's kind of like saying it doesn't have a type right now, and it can't figure out what that type is going to be. But we can say we can, I believe we can cons. Yeah, so that gives us an issue, right? We'll get to that in a bit here, but anyway. So like I said, the empty string A, the actual type is nil. So if we look at nil, right, and we look at the empty bracket, that gives us the same thing. Note that it's not quite the same. Any variable beginning with the apostrophe is a type variable, and it stands for a type that is unknown, right? That's what I was talking about. So the comma A list means the list of elements type unknown, right? And that kind of gets into this problem when we start looking at the null test. So we say null tests for something, whether or not it's null, right? So if we say null empty list, then that returns true, right? If we say null 1, 2, 3, our previous one from above, that returns false. We don't usually want to check if something is equal to the empty array, even though the empty array is null. The problem is we'll see that shortly here. But null x's should be the way you always do this type of check. So the types of lists are the type list, and then they have a specific so it's something list, right? So int list, bool list, string list, char list, whatever it might be. It's but that list is not a tuple, right? It cannot have multiple types. It can only have that type, the type of that list. So we can concatenate lists together using the at symbol. So as it shows here, we can have 1, 2, 3 at 4, 5, 6, and that gives us that. We can also check 1, 2, 3 at 4, 5, 6. We can check if that's equal to 1, 2, 3, 4, 2, 3, 4, 5, 6, and that should come out to be true, right? So we have this capability to do equality and concatenation on lists. Note that we cannot concatenate an item into a list, right? An individual item cannot be concatenated with a list because they are not of the same type, right? 2, 3, 4. Right, so if we have this, 1 is an integer, and then the other side is int list, right? So it's not going to work. The at symbol does not work on non-list types, so that's going to give us an error. So what we actually need to do is we need to use what's called the cons operator, and so this is what I was doing earlier. So the double colon is the cons operator, and what it's basically saying is that I want to take whatever object is on the left-hand side, in this case 1, and I want to add it to the front of the list on the right-hand side, which in this case is 2, 3, 4, and that will give us that list. So this is actually a way that we can use to build lists up. And so there's different ways to do this. You can actually say, for example, we can say 1 cons with 2 cons, 3 cons, 4, and then the empty list, right? And that will build up the typical list. We can also we can also do the same thing. Let's just do 1, 2, 3, and then nil, and that will give us the same as we expected, as we saw before, except for it gives us 1, 2, 3, right? So these are different ways we can build these things up. You can cons lists into things, lists of lists. You can do all sorts of different stuff with this. So we say val x equals sharp c, so the character c, and we cons that with the empty list, and it gives us a character list containing c. We can then say val y equals sharp b, the character b. We cons that with x. Gives us y is now the characters b and c in the list, and we can do it again with val z equals the character a, cons with y, and all of a sudden we have abc, right? So the double colon is the list builder operator, allows us to build these things up. Now note that the operator takes elements of any type and a list of elements of that same type. So bear that in mind. It still requires us to build a list in the correct way using the same typed items. And as we just saw, we can build things up. Now we can also work with, so if we rename val z, right, to be the list 2, 3, and then so we have the list 1, 2, 3, right? Now we have the head and tail operators. So HD is the head operator, so that tells us what the first item is in the list, and then the tail operator TL returns everything after the first item. So in this case, it will be the remainder of the list as a list. So we can combine these operators, head and tail, in order to deconstruct a list and gain access to different parts of it. So, for example, in what they're showing here, TLZ, right, would return the last item, the last part of the list 3. At the other hand, if we said TL, actually we say head of TLZ, right, that would give us 2, the item, right? We can continue this and say TLZ, which then returns the empty list, right? Because if we looked at how we built this in the first place, was with this cons operation up here, the end of the list is always nil. So if you went too far out, you always get the empty list. So finally, we can also work with strings and convert them to and from lists. Or we can convert a string into a list of characters, or we can take a list of characters and turn it into a string. And so that's using the explode and implode operators. So exploding a string converts it to a list of characters. So hello, right? So that gives me a list of characters, HELLO. And if we take the same thing, we can say implode, right? The same thing we just saw, and it returns the string. Very easy to use, very interesting operations. So giving all the stuff that we've learned so far, the practice is then to say what is the value of each of these individual statements, or these expressions, and then what is wrong with the following expressions. Okay, I'm going to let you guys figure that out and continue on. Alright, so next we get into defining functions, and then finally after that we'll work on types and type annotations, and then we should be done for the day. Alright, so in order to define functions, we have the syntax. Basically we say fun for fun, and then the name of the function, and then the argument list. So we say fun first car s equals, so all this is going to do is say it takes in some string s, and we say hd explode s. So what we're saying is, what is the head of an exploded string s, right? So we get the first character. So if we run that on first car and we give it a string abc, so note when we take a look at this, right, it tells us what the type is expected, right? So we break this down, and the type of the function that we just created, first char, is which is saying here function, and then colon, and the type of that function is it takes in a string and returns a character. So it knows how to do this based on just the operations. So it does type inference. So we know that explode has to take in a string, right? That's the only thing it can take in. And when it does that, it constructs a list of characters, and we know the head operation takes the first item off that list and returns a character. So that's the return value, right? The overall value of this. And so that defines what s must be. S must be a string, so the explode will work. And then that tells us, and we know that head returns a character, so therefore we know that the type must be string, input of a string, mapping of a string to a char. That's what we got. And so we see that when we run this. Oh, sorry. Hello. I know I bound that. Oh, I spelled it wrong. Okay, there we go. Hello, ABC. So then it works as expected. It returns the first item, A, right? So as it says here in the slide, that it's rare that you ever really need to declare a type in ML, because it can, for the most part, infer. But there are times when you will need to explicitly declare the type, so the ML system can do the correct inference, especially when you're dealing with operations or operators that are overloaded. You may be required to describe the function, the type correctly, and we'll get that. That's the last section what we'll be talking about today. So function definition, as I said, we define a function as in using the keyword fun, followed by the function name, followed by a parameter list, and then an expression, right? And so the simplest parameter is just a single variable name, although it can be a tuple as well. Bear in mind that this is we'll get a little bit more into this in the following ML section, but for today we'll just be talking about the more basic constructs. Yeah, and then as I was saying when we were talking about the function types, that it's the return value of a function, as we said over here in is some string with the arrow and then caret. So it's some type, an arrow, and another type, right? If we were to create a function that returned took a single integer in and returned a real, then the function type that's a mapping, right? The domain of the mapping is an integer. The range is real. So, for instance, though, if we wanted to create a new one, right, that finds the quotient. So we take in two integers, right? So we say fun quote, and then now if we have more than one parameter, we need to put that as a tuple. So AB equals A div B, right? So as we can see here, that tells us that we have an integer times an integer. So a tuple of that's the tuple definition, right? For a two integer tuple that returns an integer. And then if we operate this, we say quote 6, and that returns the value 3 as expected. Similarly, if we say val pair, right? So note that the actual function quote takes in a single variable, right? Well, it's that when we say it's a tuple, we can use a tuple there as well. We can to provide the parameters to our actual call. And so that's what we're doing in this this next one. So we define a tuple pair equal to 6, 2, right? Which is the same thing that we gave quote in the first place, and then we then use that again. Right, and we see we get the same value, so it operates exactly the same way. You can pass a tuple, or so literally when you put it in parentheses, you're constructing a tuple in the first place. So you assigning that tuple to a value and then using that in its place will work just fine here in ML. So now even more interesting one is the typical recursive definition of factorial. So we create that function fact n equals, and here we will define it with if n is equal to 0, then 1, else n times fact n minus 1, semicolon. So essentially here, note that white space really is not a concern in ML. All that it cares about is that the statement is end with a semicolon. So we define that. Now we create this function factorial, which is a mapping of int to int. And so if you say fact 5 should return 120 as expected. And there it does. Alright. So we'll walk through a couple more of these, and then we'll get to the bad length one, which is interesting. So if we want to deal with a list, right? So let's say we have a function list sum, right? And it takes in a list named x. And then what we're going to do is we're going to do a null check here. So we say if null x then 0, else we're going to take the head of x, and then we'll add that to the recursive call list sum tail of x, right? Pretty simple. We essentially are going to walk the list, the one item at a time start, and then do this recursively and drilling the list down piece by piece. This is also, note that the last part of this call over here, actually this part right here, is the recursive part. This is actually what we call a tail recursive experience, a tail recursion call. It's called that because the last thing is a recursive call. Also note that typically in functional languages, the way this is actually implemented makes it so that it's as fast or faster than iteration in other languages like C or Java. That being said, we did this, so let's create a list sum 1, 2, 3, 4, 5, right? And we should come up with 15, and there it is, right? Nice, fast, easy day. So this is a common pattern, right? Using the base case null x for lists. It's very common, right? Because we're checking, is it the empty list? And then we operate using the tail of x. This is the typical list processing. It'd be very similar to using like an array copy, or adjusting the start index of the array to be one less than it was before if we were in, for example, Java. Or if you're in Python, by doing a shift on by copying the array using like, for example, :1 inside the square brackets. Anyway, finally, we can calculate the length of a list by using function length, right? And we do that and saying if null x, then 0, else 1 plus the length of the tail of x. Really simple. These are all super simple recursive functions. Almost everything that we're going to do inside of this language will be working in recursion. And so if we take this and we say true, false, true, when we execute that, we see 3, right? Length 4.0, 3.0, 2.0, 1.0. Execute 4, right? Now if we go back up here and we look at the type of the list, type of the function, it was that comma A, or the apostrophe A, right? What that was telling us is that it's some unknown type list that returns an int. So it doesn't matter what kind of list we send it, as long as it's a list of some type, right? And that's something that we need to be aware of when we're doing this. Also note that finding the length of a list in ML is already predefined, so we don't actually have to deal with that. But like I was just saying, because our type is the apostrophe A list, it's actually polymorphic, right? We create a polymorphic function without really even trying. Finally, when we were talking about that, we said we don't want to do the comparison on x equals the empty list, and there's a reason for this, is that it will work for some things, but it won't work for others, because the equals empty list is actually an equality check, and it requires an equality type. And that's what it's showing here. I'm not going to type this one in, but just so we can have an understanding, right? And that's like actually we will I won't type it in, but we'll get the same results. But here we see that it has a double apostrophe A, and so what that's saying is that the type of that is actually is a unknown type. A polymorphic type is restricted to equality types only. And so we have to bear that in mind if you see that you're not giving it information that would cause an error. So one more time to see the same exact pattern that we normally do, we will run the function reverse. Takes in some list L, right? And we say if null L then nil, right? So if we see a null list, then we return nil. Else reverse tail of L concatenated with head of L, right? So this is going to be a good times. So we go ahead and run that, and we say reverse 1, 2, 3, and we see 3, 2, 1, right? So how this is basically working is it's using the same tail recursion approach, where we are going to continually call the tail of L, and then we will go until we have null, and then if we do, we then take the head and concatenate that in the list form with the reverse call. We keep doing that until building up the rebuilding the list in reverse. Finally, ML types, right? So what have we looked at? Over this entire section, we've basically been talking about basic types, right? So this is not quite as an extensive, in-depth, how do we do all this stuff like I did in with the Ruby one. Ruby is, we could have easily done very simple and very easy day, but I wanted to, some of the stuff that we need to get to, which involved regular expressions, required you to have a deeper understanding of Ruby than I'm going to require you to have for ML. But anyway, so here we have int, real, bool, char, and string. But the more important things that we're learning from this language specifically is understanding like sort of the underlying way we think in functional programming, and how we, and as well as strong typed language. And so we have type constructors, right? The times, which is from tuples. We have the list type, and then we have the function type, which uses the described with the dash arrow, right? So we can combine these constructors, right? So when combining constructors, list has higher precedence than star or arrow, and arrow has the lowest precedence, right? And so the interesting thing is the type constructions. So if you have an int, if you have a tuple composed of an int and a Boolean list, as well as which is the same as effectively an int and a bool list, right? In parentheses, and an int, a tuple of an int bool list, a function defined mapping that to a real number is the same as the entire thing, a tuple of an int by a bool list in parentheses, right? So they're all kind of equal. The parentheses are just added for clarity. Now the interesting thing here, right, is this next function. This kind of gets into polymorphism and why we need to have type annotations. So if we did create this function fun prod a b, right, equals a times b. So we did that. It tells us that it only can take in ints and it returns an int, right? But the multiplication operator also works for reals. So the question is, why didn't ML do that? Well, it just made the first assumption. So the first thing, the default type for multiplication, plus, and subtraction is integer, right? And so the problem here is if we want to do a real version of this, we'd have to actually use type annotations to allow that to happen. And so we do that by simply saying, we say fun prod, and then in this we say a real, b real, real equals a times b, right? And the colon tells us is the way we annotate types. So we could easily, and the interesting thing about that is in reality, you don't have to do that much type of annotation. And it shows here in the slide all the different ways that you could have done this in order to show that it is an actual. It would come out where we're only doing this for reals. It's probably easier to do it the way it's shown here, or at least showing both A and B are real, than it is for anything else, because that will be inferred through the operation what the return value type of the function is. Anyway, the summary is we basically covered all the constants, primitive types, operators, conditional expression, function application, predefined functions, and then we defined types using val. We looked at tuple construction and selection using the pound I operator. Looked at list construction, type constructors with the tuple type, list type, and function type. And then we saw how to declare functions using the function, the fun keyword, as well as we looked at type annotations. So this is the basic constructs and concepts of ML. Tool around with it a little bit. On the website, you will find a few places you can go look for more information, as well as where you can go look to, and then a few more exercises that we'll be doing in class. So right now it's scheduled, as I'm making this video, there's scheduled for 2 days. I might reduce that down to 1 day to expand on other topics as needed. So anyway, I'll let you guys get back to it, and I'll talk to you in class. Have a good one.